Hello everyone, this is Rupesh. Today I'll be discussing Mesoionic compounds in heterocyclic chemistry part 2. The term Mesoionic means mesomeric plus ionic was first introduced by Baker and Hollis in 1949 to describe the structure of an N-phenyl signon as a resonance hybrid of the dipolar resonating structures. Here, mesomeric. Mesomeric means it is defined as the polarity produced in the molecule by the interaction of two pi bonds or between a pi bond and lone pair of electrons based on an adjacent atom. So these are the resonating structures. This is the resonance hybrid of the dipolar resonating structure, which is also called as phenyl signon. That is, phenyl is attached to an heteroatom, so N-phenyl signon. Signons were the first mesoionic molecules. As I said before, a N-phenyl signon is the first mesoionic molecules subjected to detailed study and are named after the University of Sydney, where they were first prepared by Earl and Mackay in 1935. Signases are generally prepared by dehydrative cyclization of N-nitrosamino amino acids, which are synthesized by N-nitrosation of amino acids. Signon derivatives have been extensively studied for their biological activities such as antibacterial, anti-tumor, anti-malarial, anti-inflammatory and anti-hypertensive agents. What are actual mesoionic compounds? A 5 or 6 membered heterocycle which cannot be represented satisfactorily by any one covalent or polar structure and possesses a sextet of electrons in association with the atoms comprising heterocyclic ring. But the term mesoionic has been restricted to the 5-membered heterocycles, and the definition of mesoionic heterocycle has been modified now as a 5-membered heterocycle which cannot be represented satisfactorily by any one covalent or polar structure and possesses a sextet of electrons in association with the 5 atoms, which is very important, 5 atoms comprising the ring. That is an heterocyclic compound containing a 5-member ring. The mesoionic heterocycles can be represented by a general formula where A, B, C, D, E and F F are atoms or groups of atoms derived from carbon or heteroatoms. The heterocyclic ring bears a fractional positive charge which is balanced by a corresponding partial negative charge located on an exocyclic atom or group of atoms covalently attached to the ring through an carbon atom. That is, this A, B, C, D are an carbon atoms or it may be a hetero atoms. This is an exocyclic atom which is attached to the carbon of the heterocycle. This is an example of an mesoionic compound, whereas this is not an example of an mesoionic compound, because in this there is an external salt in which a positive charge on the nitrogen is balanced by counter ion which is an iodide, whereas in this an heteroatom, this is an exocyclic heteroatom attached to the carbon of the heterocycle, whereas no such heteroatom, that is no such exocyclic atom is attached to the carbon. This is an counter ion which is balanced by the positive charge. Coming to classification, Mesoionic heterocycles can be divided into two general classes, type A and type B, depending upon the contribution of electrons by the ring atoms to the pi electron system of the ring. Coming to the first one, type A mesoionic compound. Type A mesoionic heterocycles in which each of the two non-adjacent atoms of the 5-member ring contributes 2 electrons to the pi electron system are referred to as a type A, and this is represented as, you can say this is a type A mesoionic compound where this is the two non-adjacent atoms, okay, which contributes 2 electrons. You can see this is a two non-adjacent atoms which contributes 2 electrons to the pi system. These two contributes 2 electrons, whereas B, D, E, F contributes 1 electrons. Coming to type B, mesoionic heterocycles in which each of two adjacent atoms of the 5-member ring contributes 2 electrons to the pi electron system are known as type B and represented as this. You can see here there are two adjacent atoms which can contribute 2 electrons. Remaining all the 4 atoms can contribute 1 electron each. And this is a general representation of an type B. The two general types of mesoionic heterocycles, as type A and type B, exhibit quite distinct chemical properties. Type A mesoionic heterocycles participate in 1,3 dipolar cycloaddition reactions, as these heterocycles are regarded as being derived by the combination of, that is, addition of 1,3 dipoles, this is 1,3 dipoles and heterocumulanes to get, there is a type A mesoionic heterocycles. The important chemical property of type B mesoionic heterocycles is their fissile ring opening to provide an acyclic valence statomers. This is an acyclic valence statomers. Whereas this negative charge shifts here to form a double bond. This double bond shifts here to form double bond between B and A. This breaks and this forms double bond here, and this neutralizes to form this, to form an acyclic valence statomers. Now coming to the chemistry of mesoionic heterocycles of type A, 1,3 oxazolium thiolates undergo 1,3 dipolar cycloaddition reactions with a number of dipolarophiles. This is and 1,3, you can see, and 1, 2, 1, 2, 3. Hence 1, 3. This is an oxazolium compound heterocycle. 1, 3 oxazolium, and olate is in the 5th position. Hence it is called 1, 3 oxazolium thiolates, which can undergo a cycloaddition, especially at 1, 3 dipolar cycloaddition reaction, the number of dipolarophiles. This is a general representation of 1, 3 oxazolium thiolates. And you can see there are at the 1 and 3rd position there are 2 1 and 3rd were dipolar, 2 poles. Reactions with, coming to the reactions, starting with alkenes, 1, 3 dipolar cycloadditions of 1, 3 oxazolium thiolates to alkenes result in the formation of bicyclic adducts, which on heating carbon dioxide is eliminated readily with the formation of final products via 1, 3 dipole. As I said, this is 1, 3 oxazolium thiolates which reacts with alkenes, which is a dipolarified, to give a bicyclic adduct. This on elimination of carbon dioxide, that is, this bond forms a double bond O, and this bond breaks to form a negative charge here. It is here, and here there is a formation of positive charge. This is an bicyclic adduct. On elimination, we get a final product which depends on the dipolar. Here I took a general one, that is a double bond. I haven't mentioned what is X and Y. Coming to the example 1, the cycloaddition of 1,3-oxazolium 5-olates with styrene affords 2 pyrrolines. This is 1,3-oxazolium 5-olates. This is a dipolarified, which is a styrene here, which forms a bicyclic adduct. That is, in negative shifts here to form a double bond. This double bond comes and attacks here, and this double bond goes and attacks here, which possesses a positive charge. Hence we get this. This on heating, or this loses a carbon dioxide with the formation of 1,3 dipolar, and this negative charge abstracts a proton here, and this shifts here to form a double bond and neutralizes a positive charge, that is a tautomerization. We get 2,3-dihydropyroles. Coming to the next synthesis, the reactions with alkynes. 1,3-dipolar cycloaddition of 1,3-oxazolium 5-olates with alkynes results in the formation of pyrroles with the elimination of carbon dioxide. The rate of cycloaddition is increased if alkyne is activated by electron withdrawing substituents such as ester, nitro group or cyano group. This is 1,3-oxazolium 5-olates reacts with alkynes, which results in the bicyclic adduct. This loses a carbon dioxide to get this compound. This is pyrrole. That is, this bond shifts here to form a double bond O. This bond shifts here, and this bond shifts here to form this one. Coming to the next route, reactions with isothiocyanates and isocyanates. Cycloaddition of 1,3-oxazolium 5-olates with phenyl isothiocyanate results in a new mesoionic species, which is 1,3-diazolium 5-thiolates involving an initially formed bicyclic adduct. Here this is 1,3-oxazolium 5-olates reacts with phenyl isothiocyanate. This is phenyl isothiocyanate. These two reacts to form a bicyclic adduct here, and this is negative charge moves here. This double bond comes and attacks here, and this bond goes and attacks here to form this one. This loses a carbon dioxide to get this one. But with isocyanates, that is 1,3-oxazolium 5-olates reacts with isocyanates to get a bicyclic adduct, which is a stable one. See, this is a new, as I said, is a new mesoionic compound. That is, not only a conversion, not only addition, this can be converted to olate to thiolate. Coming to the chemistry of mesoionic heterocycles of type P. Coming to the first route, that is using thermal isomerization. 1,2-diazolium 4-arninides undergo thermal isomerization. This is aminides undergo thermal isomerization when heated in benzonitrile with the formation of isomeric pyrazoles. This is 1, 2. This is a type B. Hence, this is adjacent atoms 1,2-diazolium 4-aminides. 1, 2, 3, 4 aminides undergo thermal isomerization in the presence of benzonitride to give pyrazoles. That is, this negative charge takes this attacks this methyl group with the formation of a double bond here to get this. This carbon possesses a positive charge. This negative comes and attacks this methyl group. This bond shifts here to form a double bond. Coming to the next method, reaction with DMAD, that is dimethyl acetylene dicarboxylate. 1,2-diazolium 4-aminide reacts with DMAD in the presence of acetonitrile in the formation of pyrazoles. That is, this negative charge attacks here, and this one of the multiple bond goes and takes the proton. This reaction run in an acidic condition to form a pyrazole derivative. Coming to the synthesis of mesoionic heterocycles of type A, starting from N-acyl amino acids. 1,3-oxazolium 5-olates are synthesized by cyclodehydration of N-acyl amino acids with acetic anhydride at low temperature. And you can see this is an amino acid. It is acylated at the N position, hence it is called N-acyl amino acid. Reacts with acetic anhydride to give the mixed anhydride. Lone pair on oxygen attacks this carbon, and an acetate is eliminated to form this one. This is a mixed anhydride. Again, the lone pairs on nitrogen shifts here to form a double bond, and this double bond attacks here with the elimination of one more acetate molecule to get this one. The eliminated acetate molecule abstracts this proton. This forms a double bond here, and this forms an exocyclic atom, that is olate, O minus, to form 1,3-oxazolium 5-olates. Coming to the next synthesis, 1,3-oxathiolium 4-olates are unstable and are generated in situ by cyclodehydration of the acids using acetic anhydride. This is a thio group. This on reacting with an acetic anhydride, we get 1,3-oxathiolium 4-olates, and this is an unstable, and this is the same mechanism which as follows as the first one. From dithioglycolic acids, 1,3-dithiolium 5-olates are prepared by cyclodehydration of dithioglycolic acids with acetic anhydride at low temperature. This is an dithioglycolic acid, reacts with acetic anhydride at low temperature to give 1,3-dithiolium 5-olates. The mechanism follows as the previous examples. Coming to the next one, from N-nitroso alpha amino acids, 1,2,3-oxadiazolium 5-olates, which is a signone, as I said before, are prepared by cyclodehydration of N-nitroso alpha amino acids using acetic anhydride or TFAA, trifluoroacetic anhydride, as a dehydrating agent. This is an N-nitroso alpha amino acid. N-nitroso is attached to an N of the amino acid, hence it is called N-nitroso amino acid. Reacts with acetic anhydride to form this one. A lone pair on oxygen attacks this, and acetate is eliminated to form this one. This is a mixed anhydride. Here the lone pair of nitrogen shifts here, and this double bond shifts with the elimination of acetate to form this one. This is an 1,2,3 oxadiazolium 1,2,3 oxadiazolium 5-olate. Mechanism as follows the previous example. Coming to the synthesis of mesoionic heterocycles of type B. From dithiazone 2,3-diphenyl 1,2,3,4 tetrazolium 5-thiolate is prepared by oxidation of dithiazone with manganese dioxide or sometimes with isoamyl nitrate. This is an 2,3-diphenyl. This is a dithiazone. Here the lone pairs on nitrogen attacks here. This shifts to form a double bond. This forms a thiol. This is actually dithiazone. This on oxidation with manganese oxide, we get this one. That is, it gets oxidized here. The lone pairs on nitrogen shifts here with the elimination of hydrogen. We get 2,3-diphenyl 1,2,3,4 tetrazolium thiolate. From next synthesis starts from dimethyl hydrazine. N and dimethyl hydrazine undergoes condensation with 2-acetoxy 1,3-diphenyl propane 1,3-dione followed by treatment with aqueous sodium hydroxide to give 1,2-diazolium 4-olate. This is an 2-acetoxy. This is 2-acetoxy 1,3-diphenyl propane 1,3-dione, which gets acidified to get this one. This on condensation with N-dimethyl hydrazine to get a cyclic 5-membered cyclic product. This reacts with NaOH. NaOH abstracts a proton here to form double bond with the elimination of an water to give this one. Here the lone pairs on nitrogen forms a double bond and this OH minus is eliminated to form an nitronium ion, so N plus. Here again one more molecule of base is added. This attacks a carbonyl carbon with the formation of an olate, which is 1,2-diazolium 4-olate. Coming to the applications, 1,3-dipolar cycloaddition of alkynes to type A mesoionic compounds forming 5-membered heterocycles via bicyclic adducts has proved to be a valuable and important synthetic reaction. Many novel heterocyclic derivatives of pyrroles, furans, thiophene, pyrozoles and isothiazoles have been synthesized in high yield by using this route. Another attractive facet of the method is that the type A mesoionic substance need to be isolated but can be generated in situ from its acyclic precursor in the presence of alkynes. A wide spectrum of biological activities such as antibacterial, anti-tumor, anti-malarial, anti-inflammatory and anti-hypertensive agents have been extensively studied, which is like a signome. This is all about mesoionic compounds. I will see you in the next class with a different topic. Thank you.